Here, we're talking about Taylor polynomials and approximation tool. That's how we're going to talk about it today. If you want to go watch, there's 3 videos on AP Classroom, 10.11. In our book, it's 8.7. Here's all the numbers so you can find all your stuff. I'm going to start with e to the x, which is this graph. I did not print in color, but if you want to color on yours, you are more than welcome to. So e to the x is the one without the arrows, obviously. It looks exponential. I put a dot at x equals 2 because that's the tangent line that I have. And up to this point, what we've done is a tangent line approximation. So this picture is meant to be e to the x with a tangent line approximation of values around 2. So this is actually, and I didn't put this up here, so we could call this for x equals 2. And so this over here, y equals e squared plus e squared x minus 2. This is the y-intercept. That can be the y-intercept because that's not positive. I don't know. I'll put that in there. Maybe it's negative. You got all the colors? Okay. All right, so this would tell us about values near 2. 4 values near 2, like f of 2.1. We could plug that in, and we would get, this should be negative e squared, I think.
Wait,
Sorry, I think that's negative e squared. In order to have a y-intercept that's down here, it would have to be negative e squared. My bad. I'll just put a negative there. Okay, so this approximates values near the point 2e to the 2, right? If you plug in 2 into e to the x, you'd get to e squared, which is the y value, which is why this one should be negative. My bad. Because when I put it to the other side, it should be negative. All right, so what we want to do is, what if we want to approximate other values, like f of 4? This would not be a good graph for that because look at 4. My tangent line is going to be up here. My e to the x's, they're far apart, right? So what Taylor polynomials are going to do for us is they're going to let us approximate with things that aren't tangent lines. So this is a linear equation. This is x to the first degree. Good morning.
Morning.
So this is a first degree tangent line. What if we found a second degree? It's not really tangent. We're trying to approximate better than a line. So we're going to be able to approximate with shapes that are closer to the function e to the x, which is a transcendental function, with other polynomials. So this is called Taylor polynomials, meaning, Ben, we're right here. Meaning that we're going to have many terms, right? Polynomial, we're going to have constants, first degree, second degree. See how this second degree one? Yes?
For some of the, like just the stuff on the top, I think I got it really nicely lost.
Okay.
You put a negative next to the.
I put a negative because look right here. This is the point 2, e to the 2. If I write y minus y equals x, slope m minus x, I said that backwards. If I write y minus y equals m x minus x, this should be negative e squared. Oh, it should be positive. Oh, I'm right. Okay, sorry. Thank you.
Erasable pen.
Erasable pen. Figure it out.
I'm making it a positive. I just overly specified what I need is positive now.
Oh, because that would multiply it by negative 2, and then it would be negative. Okay, my bad. Sorry. I was trying to make the negative work for my y-intercept. Hold on, Rachel has a question. What?
So it's positive.
It should be positive.
Okay.
Yes.
Why would we use a Taylor polynomial to approximate when we could just use the actual thing?
Because we're going to lead from here into purposes of series that we just did our stuff.
Oh, okay.
And for some things, it's easier to take a derivative of a polynomial.
Okay.
And so if we can approximate with a polynomial, we can get there. Also, if you watch the video that I posted about pi, it's all about how it took them, I don't know, days, weeks to figure out pi. Like when they finally were like, okay, I'm going to take my circle and I'm going to divide it into not 6 pieces to approximate the circumference, but like as many as I can do by hand, would take them days and days and days to do the calculations. When they figured out that they could do an approximation like this, it just maybe took them a couple days versus months. So this is a way to approximate better, and it's actually really cool. So this is for being able to do things by hand. I know E squared is hard by hand, but that we would have trouble doing otherwise. Sometimes the math is the tools. This is a tool. We're learning the tool. We're on this picture now. Does this picture with the parabola that's this guy, if you were to make it a color, with the arrows on it, the arrows is the one that's the approximation. Does it model e to the x better? Especially near 4.
Definitely, yeah, definitely better.
The line with the arrows, you said, is the approximation.
The line with the arrows is the approximation. Then the next approximation in the little box, what degree is it? Third. So this is the highest degree in the one on the left. Third is the highest degree on the one to the right. And it is almost the same as we get closer and closer on this side. So it would be a better approximation for numbers that are further away from 2. And I think given this image, we can all see it. And what's cool about this is that it looks a lot like what we did with the linear approximation. And we're going to talk about how these different terms come about being. But it has the same form basically. I want you to notice that since 2 right here, x equals 2, was our first tangent line, all of these values have this x minus 2 in them. Because 2 is where we started our original problem, and we're going to call that our center. Okay, so this is centered around 2. Now, in our very first tangent line, now that we've fixed my math, and I shouldn't have overthought the positive e to the x. I mean, I did this myself, so I took the equation that I had graphed, but whatever. This is the this is the y value of our center, not the y-intercept. This is slope, e squared, because how do you take the derivative of e to the x? You get
X e to the x.
e to the x again, and you plug in 2. That's the slope at 2. So this is slope. Okay? What's the second derivative of e to the x? The derivative of
X squared.
No. So we got y equals e to the x. Y prime equals
E to
e to the x.
Oh, yeah.
Y double prime equals
E to the x.
e to the x. Any prime is going to be?
E to the x.
Isn't that cool?
That is.
Okay, so if I'm finding any of these slopes of slopes, and I plug in 2 because my x value is 2, it's centered at 2, they're all going to be the same. Do you see that sameness represented in my equations? This is slope. This is actually the same slope, right? This is the same equation up to here, this first box. This is going to be slope, and this is going to be slope, but they turn out to be next derivatives.
What?
So we're going to look at that in a second. So we're doing the same thing that we did before with a tangent line approximation, but we're saying, hey, if we want our polynomial to have the same shape, then in order to have the same shape, its first derivative needs to be the same. Its second derivative needs to be the same. Its third derivative needs to be the same. Like all of the slopes, any sort of rate of change of slope needs to be the same for the polynomial. So that's where the rest of these come in, is this is going to be, and I have it on the next page so you can see it, but before we look at that notation, which Charlie already sort of peeked at, it's a little bit overwhelming and I don't want that to freak you out. This is the first slope. This is f prime of x. This is going to be f double prime. This is going to be f triple prime. And it goes with the third degree. What would come next in the pattern?
Would it be e squared x minus 2 to the 4th over 4 factorial?
It would be just like that. So the pattern is easily recognizable once you see the pattern. As I mentioned in the second video of 10.11 on AP Classroom, they go through the proof of it. But I'm going to take you on a shorter ride. So we've already Madeline figured this out. We would have the same as up top, e squared plus e squared x minus 2. Could I put this over 1 factorial?
Yeah.
I could even put this over 0 factorial. Do you know what 0 factorial is? Just 1. So we've got e squared x minus 2 squared over 2 factorial plus e squared x minus 2 cubed over 3 factorial plus, and it just keeps going. For this particular problem, they don't all do this quite the same, right? Because they don't have the same derivative. E to the x is special, it has the same derivative. So the other ones, if we were going to do a different problem, which we will today, they're going to have different derivatives there, but the pattern is easily recognizable. Now, the factorial, we've done a little bit with factorials with our series stuff. Where does that come from? Y factorial. Have any guesses?
Wait, so if 0 factorial is 1, then how is 1 factorial also?
Because 1 is times itself. So this is like a basic, this is a rule, like in order to have factorial, we're going to say 0 factorial is 1.
Okay.
And then 1 factorial is just 1 times 1. And then this is 2 times 1. And this is 3 times 2 times 1. And this is 4 times 3 times 2 times 1. So we want to know why this, just for a second, so this will make sense. Let's take for just a second, let's take a very, 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 very basic polynomial. If we said x plus x squared plus x cubed plus x to the 4th plus x to the 5th. I'm not going to have enough room to write a whole bunch of derivatives on this particular paper. This is my y equals, because I'm going to run out of space. But when I take the first derivative, what happens? What do I get for this?
Oh, because it comes in the front, so
That one's just 1, right?
That one's 2x.
And so this one's 2x, and this is 3x squared plus 4x to the 3rd plus 5x to the 4th. Yeah, but then the next one, so y double prime is going to be 0, and then 2 plus, and then this one's going to be 3 times 2, right?
Yeah.
3 times 2, so that's 6. I'm going to write 3 times 2x plus 4 times 3x squared plus 5 times 4x cubed. Do you see the pattern yet?
Yeah.
I don't have room to write it, but the next one would be 4 times 3 times 2, and then it would be 5 times 4 times 3, right? So every time you take a new derivative, you're going to have this cascading, if you will, number, and that's equal to the coefficient right here, this e to the x, and we're going to see that in our next problem. So what I'm telling you so far is that the linear approximation is great if you're looking at values right around the value that's centered. So C is going to be our center value, and that's going to be given to us in a problem. But if we keep going and don't make it a tangent line, if we make it a polynomial approximation, it's going to have more pattern that's going to match your original graph. Okay, page 2. On page 2, I've got 2 general forms for what it looks like. And we want to talk about vocabulary a little bit, so we're on the same page. We're looking at the basic lineup of what a Taylor polynomial looks like. this a sub 0, this is the coefficient. And that is what determines the behavior of the polynomial that's going to work. So all the polynomials are going to have like x to the first degree, second degree, third degree, but the coefficients in the front come from the derivatives. So this coefficient is from, this is f prime of x, because it goes with the linear approximation. Do you see the linear approximation now? Right? So this is like the y value. This is slope times x minus c. Do you see what I'm saying? So this must be from the second derivative, and that's why we have 2 factorial from what we just did a minute ago. This is going to be from f triple prime of x. And it would keep going, and we're familiar with series. We've written out things like this for the past couple weeks. This last term, you already told me I'm going to write as a sub n x minus c to the nth power, and then what goes in the denominator? In factorial. And so this one written underneath, it's the same exact thing. I've just written it out in function notation. So we've got, this is the original y value, original y, that's for both of these. A sub 0 and f of c, that's the original y. This is first derivative, second derivative, third derivative, you know what I mean? Okay. So both of those forms are come from taking the derivatives, and we're going to try some out in just a minute. So vocabulary. So we're on the same page. The center. How could we talk about the center?
That's like where the problem tells us to go from.
Yes.
Right?
So like that first tangent line point, it's the value we want to match our polynomial to. So on the other page, we had x equals 2. That's where it started matching up with our e to the x. So I've got the value we want to match our polynomial. The value we want to match the polynomial to the function given. So the center value. So they're going to ask us, they're going to tell us what that is. The degree is how good of an approximation do you want to get? The higher degree you have, the better approximation you're going to have. Our tangent line approximation was great for values right around the center, but we're going to find better approximations with our Taylor polynomials. So this is the degree of the polynomial for approximating. I don't know that. The degree of the polynomial for the approximation.
I like handout notes.
Well, that's a lot of writing.
Mm-hmm.
That function is a lot of writing.
And you said the higher the degree, the better the approximation.
Yep, higher degree. Better approximation. So the function is the one we're trying to approximate. So this is given. Other words used might be the function you want to clone. The one you are trying. So instead of approximate, you could say clone. Except clone it with a polynomial instead of whatever function you have. So we'll take things that are e to the x or sine or cosine and try to change it into a polynomial function to represent those values. We're going to do natural log together as an example today. Notation, so this n means the degree, where we're going to stop with our n, the degree of the approximation. So P would be polynomial of degree n, T would be Taylor approximation. Either one are sort of, you know, base values for what we might call our stuff.
Do they mean the same thing?
Yep. But these are typically used for this kind of approximation. So the difference in the style of this, normally we would write a line approximation, a linear approximation with y equals mx plus b and have that at the end. But as a note, because we could be adding extra degrees at the end, these are sort of formatted differently. So it starts with a constant term. This is just f of whatever the value is from the function. So that's our starting place, right? That's the original starting value. So on this, well, yeah, it is. It's the original starting value once you move to the other side. After that, each coefficient is the next derivative. So each coefficient is the next derivative. I'm just saying that again because we haven't done that yet and it may not be familiar to you. And then it's going to be multiplied by x minus the center because that's the shift. We're not doing 0 necessarily all the time. And then the next degree over that degree. I don't know why I wrote it out like this. I just was thinking that that made sense to me at the time. But if you get the value, the way that it's written up here in these two examples, you're good to go. The degree factorial comes from successive derivatives. So the degree matches the number on the bottom. But this part, x minus center, stays the same all the way through. If you're asked for a Maclaurin series, that one has a center value of 0. It is still a Taylor polynomial, but it just has, instead of x minus c, you just have x, which is definitely handy. So this is similar to when we did mean value theorem and Rolle's theorem. Rolle's theorem was when the derivative was 0. This is just a specific case where the center value is 0. Okay, we ready to try some?
Sure.
Excellent. Okay, so I started as a chart. I've got the same two equations at the top, so we have them for reference. And I'm thinking of these as the coefficients.
Miss Kate,
Yes?
on the back page, what did we write? I don't think we wrote for under the approximation up top for this one right here.
So it would be f to the nth derivative of c,
Okay.
x minus c to the n over n factorial.
Thank you.
Yep. There it is.
That just makes sense.
Yeah.
Wait, what was it?
Here it is.
Sorry.
You're fine.
It's also on the page.
It is. It's on the next page. Yep. But I left a space there so we could write it and talk about it because it's interesting to write f and then n as a derivative like that. It is sort of weird notation. Yeah.
You're not raising f to power.
Right. Okay. So here we go. These a's represent the coefficients for each term. So the very first one is just going to be the value, and I haven't talked about this particular problem yet. I'm just trying to explain my chart. And then I'm going to take derivatives, and then I'm going to plug in the value that they gave me as the center. So the problem for example 1 says, find the Taylor polynomials p sub 0. So that would just be a point. And then p sub 1, p sub 2. So that's actually different graphs. So this would go through 0. This would be a linear, right? This would be a linear polynomial. So it's not just a value. It would actually have enough to make a line. This would be a quadratic, a cubic, a quartic, different approximations, and then we can compare them. So I've got different graphs that we can draw on at the bottom and see what they look like. See how they get better as we find more stuff. So again, find the Taylor polynomials. We're doing the natural log of x, and we're centered at c equals 1. So we're looking at this point, and you could very easily draw in a tangent line and know what that looks like.
To see that for a second.
Okay, so we've got, this is our actual value. First derivative times x minus c. The second derivative has our new value. We found the second derivative value. And we're still going to have, so minus 1 parentheses x minus c squared. That does not work. And then this is divided by 2 factorial, which is hard to put in here, so I'm just going to put 2 because that's 2 times 1. And then graph it from the line to this. It follows it a little bit with a parabola. So this one kind of looks like, can you see it? Is it dark enough?
It's not the best.
It goes like this. So it follows it, not just this line, it follows it a little bit with the curve. And I'll change the color when I graph it for the next one. So we have a little bit better approximation. To make our polynomial have more terms, we need to take a third derivative. So what's our third derivative? X to the negative 2. So
2x to the negative
2 x to the negative 3, so 2 over x cubed. So f triple prime of 1 equals 2. So p sub 3 is going to have all the same stuff. 0, 1 x minus 1, x minus 1 squared over 2 factorial plus 2 x minus 1 cubed over 3 factorial. So this is negative, and we multiply it by negative 2. We get positive 2, which is why I rewrote it like this, so I'll try not to get lost. Yeah. Okay, so now I'm going to add that there. I'm going to keep my same equation, just add more nomial. So plus 2 parentheses, x minus c, which is 1, cubed, divided by 3 factorial, so that's 3 times 2 is 6. And then I said I was going to change the color, so I am. Okay, color, blue, that should show up.
Is this supposed to be 0?
Oops, now it's dark gray. So that little 0 thing, it draws a line as we graph it. It's fun.
Oh, is that what you did before?
Mm-hmm. So it follows the curve up a little bit. So it kind of follows this down part, and then at about 2, it kind of goes up.
That's an even worse approximation.
I think it's just worse because of my drawing. So fourth is going to be, do it again. So that's going to be negative 6 over x to the 4th. Plug in 1. That's a great thing to plug in. Love that. Negative 6. So we've got 0 plus x minus 1 minus 1 x minus 1 squared over 2 factorial plus 2 x minus 1 cubed over 3 factorial minus 6 x minus 1 to the 4th over 4 factorial. Note that when you look at the examples in the book, they don't have like 2 over 3 factorial. They've dropped the 2 because 3 factorial is 3 times 2, right? Mm-hmm. And so they dropped the 2 and just have 3, period. And here they simplified the 6 and the 4. I'm just going to leave it out so that I haven't lost you any with the derivative part. So now I'm doing the same thing at the end. Now I have a 4th degree minus 6 parentheses x minus the c value to the 4th power divided by 4 times 3 is 12 times 2 is 24. Okay, so now graph. There's the natural log. That is not this better. Is it better?
Put it in parentheses at the top part.
Did I miss something?
Yeah.
Sometimes in the calculator, if you don't put parentheses between stuff,
Yeah, the fractions, like when you put divide by 6, like sometimes it doesn't do that.
yeah, you have to put 2 plus 2x.
Yeah, but order of operation wise, it's 6 times that divided by 24.
Yeah, it should.
Normally, I just
Sometimes the calculator's
Yeah, I just put extra parentheses. Yeah. Or I do alpha x.
Conveniently, for time's sake, I do already have it printed somewhere. Oh, it is. It's just harder to see, I think, on my calculator. Okay, so here's me graphing on Desmos.
Desmos. Oh yeah, that looks.
Okay, so here it kind of has this same behavior here. This is a little bit down. And then this is just like right there. So it just stretched a little bit and a little bit more. I mean, it's hard to make a polynomial go flat. So maybe not the best to see, but we have it written out just like we're supposed to. Note what I was saying before, this could be 4 times 3 times 2 times 1. You could cancel the 6 and the 3 times 2. You could write it a different way if you needed to. Okay, time-wise, we don't have time to do the last one, which was sine. Can't find it on mine. Do I have sine? I swear I gave y'all sine.
It's on the back.
Okay. Well, I don't seem to have it on mine. Anyway, sine is really cool because it's going to end up the tangent line at pi over 6. Pi over 2 is here, so pi over 6 is like here. It ends up when you get a bunch of different nomials, it has this U shape, right? So it went from a line to a U shape. This example is in the book, and so you can look through that to see what it is that you need to do. I don't already have this written out, but this chart is what I need for you to look at, right? So if we could do part of this quickly. Sine of x, first derivative, sine of x.
Cosine of x.
Cosine of x. Second derivative, negative sine of x. Third derivative, negative cosine of x. So these are going to have the same values, like alternating back and forth between positive or negative. So sine of pi over 6 is the square root of 3 over 2. Cosine is a half. Wait, did I do that backwards? I did it backwards.
Oh.
Yeah, I can't do it.
I'm sorry. Sine, this is really the point square root of 3 over 2, 1/2. So it's really 1/2 square root of 3 over 2. And then negative would be negative 1/2 negative square root of 3 over 2. And these are the coefficients for our polynomials. And once you know those, you can pretty easily get your polynomial written out. I guess I do actually have 1 second to do it. I've got 1/2 plus square root of 3 over 2 times x minus pi over 6 over 1 factorial minus 1/2 x minus pi over 6 squared over 2 factorial. And then I would do this last one, minus square root of 3 over 2 x minus pi over 6 cubed over 3 factorial.